Okay. So in week 7, we have what are called equivalence of matrices. What are equivalent matrices? So equivalent matrices you can define for any two matrices of same order. First condition to define equivalence matrices is that we need two matrices which are of the same size, right? So we need here we are considering two matrices A and B which are of order m by n, right? Now we say that A is equivalent to B if we can find invertible matrix P of order n by n and Q of order m by m such that B is equal to QAP. So this is the definition for equivalence of matrices, right? So just to quickly recall what are equivalence, why this is a equivalent matrix, because it is satisfying an equivalent relation here. What is that equivalent relation? So the relation is that, so it is reflexive, symmetric and transitive. Reflexive means it is related to itself, and symmetric means if A is related to B, then B is related to A, and if A is related to B and B is related to C, then A is related to C. Okay, so I won't be very talking about it in very detailed manner, but quickly we can see A is equivalent to itself. Why is that so? Because we can write A is equal to A I A I, right? So we can write this, right? So here identity matrix of order M and identity matrix of order N, right? And if A is equivalent to B, then B is equivalent to A, right? This also you can easily see. Why is that so? Because if B is equal to QAP, if B is equal to QAP, then you know that Q inverse B, P inverse is A, right? So now instead of Q and P, we are having Q inverse, P inverse here, some invertible matrices, right? So A is equivalent to B, then B is equivalent to A. And A equivalent to B, B equivalent to C, then A is equivalent to C. This also you can see it very easily. So because of this, this is an equivalence relation. Okay. So the equivalent matrices, this concept is that satisfies the equivalence relation properties. Okay, fine. So in general, finding this P and Q, this invertible matrices P and Q is very difficult. Okay, it's not that easy to find this P and Q. Okay, but in some cases, we have some specific ways. Okay, so here is an example. For example, you see, for example, if we have a transformation T from V to W, okay, and we have a basis beta 1 and beta 2, which are ordered basis for V, and gamma 1 and gamma 2 ordered basis for W. Okay, and A is a matrix representation of T with respect to beta 1 of V and gamma 1 of W. Similarly, B is the matrix representation of T with respect to beta 2 of V and gamma 2 of W. Okay, so A and B are two different matrix representation with respect to different bases. In that case, we can without any verification, we can straightforwardly tell that A and B are equivalent, and it will satisfy equivalent means it should satisfy this condition, right? And in this scenario, P and Q can be specifically found in this way. So here P is expressing the ordered basis beta 2 in terms of the ordered basis beta 1. And for Q, you have to express gamma 1 in terms of gamma 2. Okay. So then it will satisfy this relationship. Okay.
Ma'am, can you just go above once, please?
Yes. See, here what is happening here? If A and B are equivalent in this scenario, this Q and P can be found in this following way. The P is expressing the ordered basis beta 2, elements of order basis beta 2 in terms of the elements of beta 1. Okay. Same way for Q, you have to express gamma 1 in terms of gamma 2. So with these coefficients, you can make the matrix P and Q. Is that fine? Yeah.
Okay. Okay.
Yeah. So what are the important characteristics for equivalent matrices? Two matrices A and B are equivalent if A can be transformed into B by a combination of elementary row and column operations. Okay. So in general, whatever you are doing this row reduction, right? So this row reduction which you are doing in Gaussian elimination, all the matrices obtained in every step, they are all equivalent matrices because of this property, right? Because one can be obtained by a combination of elementary row and column operations, right? So whatever matrices you are obtaining in every step, they are equivalent matrices, right? Two matrices A and B are equivalent if rank of A is equal to rank of B. So you take any two matrices, first of all, remember A and B should be of same order. Just because rank is same, the matrices cannot be equivalent. Remember, they should be of same order, then only you can define equivalence relation. Okay. So two matrices A and B are equivalent if rank of A is equal to rank of B. Okay. So if they are of same order and their ranks are equal, then they are equivalent. Okay. So just like equivalent matrices, we have something called similar matrices, which are having a much stronger condition. So what is that? So A and B are said to be similar if we can find an invertible matrix P such that B is equal to P inverse AP. Okay. So instead of any invertible matrix Q, here specifically we have P inverse. And what is the difference, main difference between equivalent matrices and similar matrices? Equivalent matrices we can define for rectangular matrices, but similar matrices is defined only for square matrices. Okay, so similar matrices cannot be defined for rectangular matrices, only for square matrices. Okay, and here you have P equal to P inverse AP. Okay, so obviously similarity implies equivalence, right? Instead of P inverse, you just put the name Q for P inverse, then you see that the condition for equivalence matrices is satisfied. So similarity is always implies equivalence. Okay, and just like equivalence condition, so this also satisfies the equivalence relations, that is the reflexive, symmetric, and transitive. Okay, fine. So as I told you, if two matrices are similar, then they are also equivalent. What about the converse? What is meant by converse? So suppose two matrices are equivalent. Let us talk about the square matrix case. Okay. So if two square matrices are equivalent, does that imply that A and B are similar? It does not. Okay. It does not imply A and B are similar. Here is an example. So look at this. A is equal to 1001, B is equal to 1101. They are not similar. How can we say that they are not similar? Suppose let us assume that they are similar. Then what happens? So similar means you know that B is equal to P inverse AP. Now, what is your A? What is it?
Identity matrix.
Yes, it is the identity matrix. So P inverse IP becomes simply P inverse P. And according to the definition of inverse of a matrix, this is again identity. But is B equal to identity?
No.
No, right? So, but B is not equal to identity. So, A and B are not similar. But are they equivalent?
Yes.
Why? Because what is the rank of A?
1.
Yeah, rank of
Sorry,
A.
2.
Yeah, rank of A is 2 and rank of B is
2.
so they are equivalent.
Ma'am,
Yeah.
for equivalence, other than rank, what can we check, ma'am? Determinant?
Whether you
Not
can obtain one as elementary, you can apply some elementary row operation or column operation and see whether you can get it. So the usual method is checking rank only.
okay. Rank and next one is elementary operation, right?
Yes, yes.
Okay, okay. And ma'am, okay. And rank and determinant is for ma'am similarity, right? Like if we can go ahead for similarity or not, right?
I will tell you. The
Okay,
next
okay.
slide is about that only.
Rank. Okay, ma'am. Okay.
Okay, so just like we saw the scenario in the case of equivalent matrices. So suppose you have a linear transformation T from V to V, and you have two bases, beta for V and gamma for V. A is a matrix representation with respect to beta for both domain and codomain, and B is a matrix representation with respect to gamma for both domain and codomain. Remember, here A is with respect to same basis for both domain and codomain. Similarly, B is matrix representation with respect to same basis for both domain and codomain. But in the case of equivalent matrices, the domains are the bases are different for domain and codomain. Okay, fine. So A and B are similar. In that case, you see that A and B are similar and it satisfies this relation. Again, here for P, you have to express the ordered basis gamma in terms of beta. So once you have P, you can easily find P inverse. Okay. So what are the properties of similar matrices? If two matrices are similar, then they have the same rank, same trace, same determinant. Okay. So if A and B are similar, then they have same rank, same trace and determinant. What about the converse? What is meant by converse here? Suppose there are two matrices of same order and they are having same rank, same trace and same determinant. Then does it imply that they are similar? Does it imply that they are similar?
No, ma'am.
No. Again, you can use the same example here. So what is the trace of these two matrices? Trace of A is equal to trace of B is equal to
2.
what is determinant of A?
1.
What is determinant of
1.
B? 1. Both are same. So here you see that you have same rank, same trace and same determinant, but these two matrices are not similar. Okay, so similar matrices can have these properties, but this properties does not guarantee that the matrices are similar. Okay, but in the case of equivalent matrices, so equivalent means the rank is same means they are equivalent. Okay, in the case of equivalent matrices, but for similar matrices, we don't have such condition here. Okay, fine.
Ma'am, once again, could you repeat how can we find out similar matrices like the P?
Okay, so in this case, what is that we are having? We are having two bases, beta and gamma. Okay, so now what we have to do? We have to express gamma in terms of the ordered basis beta. For example, suppose in case of R2, let us say your V is R2. Okay, so let us say your beta is maybe 1, 0, the usual basis, let us say. And your gamma is, let us say, 1, 1, 1 minus 1. Now you have to express gamma in terms of beta. It means what? You first of all express 1, 1. So this is kind of a straightforward case. Maybe I will write it in the reverse order. This is gamma and this is beta. Then you have to do some calculations, right? So you have to express gamma in terms of the ordered basis beta. Then what will you do? You have to express 1, 0 as a linear combination of 1, 1 and 1, minus 1. Same way, you have to express 0, 1 as a linear combination of 1, 2, 1, 1, 2, 2, 1, 2, A21, A22. Okay, this is how you have to find the matrix P in this scenario. Clear?
Yes, ma'am.
Okay. Okay, so now look at this question. So here is an exercise. So let A, B, C all are 4 by 4 matrices such that A and B are equivalent matrices. B and C are similar matrices. If A has exactly two linearly independent columns, then find the determinant of the matrix C. So what is given to you? A and B are equivalent. So if A and B are equivalent, what can you say about their rank?
Has to be same.
Yes.
Equal.
Yeah, rank of A is same as rank of B. Right? So now the next condition is that B and C are similar. So B and C are similar means you know that rank of B is same as rank of
C.
right? Also, you know that determinant of B is same as determinant of C. This is also there. Now, if A has exactly two linearly independent columns. So if A has exactly two linearly independent columns, what can you say about the rank?
Rank is 2.
2.
2.
So it means the rank of C is also 2. So if rank of C is 2, then what can you say about the determinant of C?
0.
0. Right? So if, for any n by n matrix, if the rank of that matrix is strictly less than n, then you know that the determinant of that matrix is 0. Right? So because of that property, here determinant is 0. Clear? Okay.
Yes.
Yes, ma'am.
So
Hello,
the
ma'am.
next, yes,
Where can we get this PDF?
as usual in the drive folder.
Where, ma'am?
The drive where you usually see the other live session PDFs.
Sorry to interrupt you. I'm just a little clarification. If the rank of A is less than n, then how determinant is equal to 0, ma'am?
See, determinant is, that is an equivalent condition, right? Rank of A equal to n if and only if the determinant is non-zero, right? So only when all the columns of the matrix are linearly independent, then only the determinant is non-zero. Otherwise, the determinant is 0, right? So we are talking about, suppose you consider Ax is equal to 0, this homogeneous system Ax is equal to 0. When will it have a unique solution? You can either argue in terms of rank or determinant. So when you argue in terms of rank, you say the rank should be full rank, or in terms of determinant means you say determinant non-zero. So they are equivalent conditions, right? Rank of A equal to n if and only if determinant of A is non-zero. They are equivalent conditions. Okay.
Okay, ma'am.
Okay, so look at this question now. We have to choose the set of correct options. If A is a 3 by 3 matrix, okay, similar to the identity matrix of order 3, then A must be the identity matrix of order 3. So before solving this, let me ask you this question. So suppose you have a matrix A which is alpha I. What does it mean? Can you tell me?
Scalar
Scalar
matrix.
matrix.
It is a scalar matrix.
It's scalar matrix.
Yeah. So now let us take any matrix B, okay, and say let us say that it is similar to A. Okay. Suppose this is the scenario. Then what happens? Your B is P inverse alpha I times of P, and alpha is just a scalar, so you can bring it out of the matrix multiplication and you write this. So you will simply get alpha I. So it means what? The only matrix which can be similar to any scalar matrix is itself. Okay, so there cannot be a matrix which is non-scalar and similar to a scalar matrix. Okay, do you understand what is happening here? If a matrix is scalar and if there is another matrix which is similar to A, then B should be equal to A. Got it? Okay.
Yes, ma'am.
Okay, so now from that, can you answer this? If A is a 3 by 3 matrix similar to the identity matrix of order 3, then A must be the identity matrix of order 3.
True.
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 Right? So A is specifically a scalar matrix actually, right? Where alpha is 1. Okay, if a 3 by 3 matrix A is similar to a diagonal matrix of order 3, then A must be a diagonal matrix of order 3. Is that true?
No, ma'am.
Okay. So for this, you cannot maybe generating an example is not very easy, but actually you can see that similarity you can there is this concept called diagonalization, which is a very important topic in linear algebra. That is kind of the next step of this course, you can see. So if you are going to the next level of maths after this course, then you have to see diagonalization of matrices. What does mean by diagonalization of matrices? So there are matrices which are not diagonal but similar to a diagonal matrix. That is the concept of diagonalization. Okay. So there you can see plenty of examples of matrices which are not diagonal but similar to a diagonal matrix. Okay. So generating an example here may be difficult, but you can find several examples in this case.
Them
Okay.
not diagonal but similar to diagonal.
Yes, yes. Not diagonal but similar to diagonal.
Means like one matrix is 3 by 4, another is 3 by 3, like this.
No. Same size, same size. The sizes are same here.
Ma'am, but unless and until the diagonal is same, how can they be similar, ma'am? Because the determinant would be the product of all elements of diagonal.
Okay, so if you want a specific example, then I will just have to check for an example and write it for you. So
No issues, ma'am. We can do it later.
Yeah, so this example, if you want, I can just write an example here before uploading the PDF. Okay, there are several examples which we can find easily. So in that case, for example, I can write any matrix, but I will not be able to write what is the P. That is the problem. So for example, if I write 1, 2, 3, the triangular matrix. Okay, here I can write any entry, 0, 0, something like this. Okay, so is this a diagonal matrix, or I can put any non-zero entry here? That does not matter. So 1, 1. So this is this a diagonal matrix?
No, ma'am, because
But we can find P such that P inverse 1, 2, 3. Other things are 0. What is the P? I will not be able to give now. Maybe after the class, if you want, you can find, or I can tell it for you. So you can find. Let's just stimulate several examples. I know what is the concept behind, so I'm able to write. But for you, generating such examples might be difficult. So here is an example for you if you want. Okay.
yeah, ma'am, got your point, ma'am.
Okay. Fine.
So one question,
Multiplication
sir,
it will be similar.
Sorry.
what if the question is
Multiplication P inverse
Please,
into
one by
matrix.
one. Please, one by one. Yes, Om Sharma.
Ma'am, after multiplication, like P inverse into matrix A, then resultant will multiplied with P. The matrix we obtained, it will be similar to this matrix, left side.
It will be equal to that matrix. Yes.
Yeah. Okay. Okay. Got it. Thank you.
Okay.
ma'am, what if they just you know, change the diagonal 1, 2, 3, 2, 3, 2, 1 or something?
That does not affect it. It will still, so if it is 3, 2, 1, then the diagonal entries are going to be 3, 2, 1. That's all. Or
Yes,
you can in fact,
no. My question is that if it must be is removed, and can a matrix be similar if, you know, there is 1, 2, 3 in one of them and 3, 2, 1 in the other? Can they be similar?
yes, it is possible.
Okay, it can be similar.
Yes.
Okay.
Fine. Okay. So if A and B are similar matrices, then they are also equivalent matrices.
Yeah, true, ma'am.
True.
And the second option should be wrong now.
Yeah, it is
second
wrong.
option.
Yes. It is wrong. Correct. Thank you for pointing it. Yeah. So the fourth option, if A and B are equivalent, then they are also similar matrices. We already have an example, counter example for this, right? So this is
Wrong.
No, wrong.
okay. Fine. Okay.
Ma'am, sorry for interrupting. Till now we were proving option 2 was right?
See, that is what I have given. I have given a non-diagonal matrix. So this is your A. Okay. And it is similar to a diagonal matrix, but this is non-diagonal. A is
Okay.
non-diagonal.
So in place of must, if there is can, then it would be right? Am I right, ma'am?
Yeah, maybe a diagonal. Yes, then it is. Then
Okay.
It does not make sense if you put this, because a diagonal matrix similar to a diagonal matrix, it does not make sense. But yeah.
Okay. If there is a possibility, but must is not should be used over there.
Yes.
Okay. Yeah. Clear.
Okay. So the next question here is that if determinant of A or determinant of B is non-zero, then AB and BA are similar. How to check this? So if let us first assume the first case, that is, let us call this A, B, C, D. Okay. So for A, let us first assume that determinant of A is non-zero. If determinant of A is non-zero, you know that A inverse exists. Okay. So if A inverse exists, what can you say about A inverse AB times again A? So now A inverse A, you can just pair up like this and write it. So now you see it is nothing but BA, right? So this A itself acts as your P, right? Now you should tell me what happens if determinant of B is non-zero. Can you tell me how you can prove the same? You know that B inverse exists. Then what you should do? Can you tell me?
B inverse
B inverse times BA.
Yeah.
AB.
Again,
Fine.
B.
that will give you B inverse B, AB, which is A. Fine. So if determinant of A or determinant of B is non-zero, then AB and BA are similar. Okay. So now how can we check whether these two are similar? What is their trace? What is their trace?
Trace
A
is not the
3.
same.
Equal.
Trace of A is 5 and
5 and 4.
B is 4. So they are not equal. So can they be similar?
No.
What about option
No,
C?
ma'am.
What
Trace
about
is same.
trace is same? Okay. Then what about the determinant?
Not same.
Not same.
Not same.
Determinant of A is 6 and determinant of B is 4.
It is same, ma'am.
Determinant here is 4 and here it is 6, right? How are they are same?
Okay, ma'am.
They are not equal, right? So it cannot be similar. What about the last case? This is something which we already discussed. Trace is same, determinant is same, rank is same, but they are not similar. Why?
Because B is an identity scalar matrix. So scalar matrix is similar to scalar.
Yes. So A and B are not similar, which is true. Correct? Okay. Fine. So the
Ma'am,
problem.
any non-scalar matrices.
Hmm.
Oh, sorry. All scalar matrices are not similar.
No. So if there is a scalar matrix, it cannot be similar to a non-scalar matrix. That's all.
All right.
Okay. Okay. So the next question is that if A and B are similar matrices, then A inverse and B inverse are similar. Is it true?
True, ma'am.
Right? It is very straightforward to see, in fact. Right? So how to see it? So if you know that if A and B are similar, you have that B is equal to P inverse AP. So just take inverse on both sides. Then what will you get? You get B inverse is equal to P inverse A inverse P. Right? Because you know that if you have two matrices and you take inverse, the order of the inverse is reversed, right? Because of this property, you will still have P inverse A inverse P. Right?
Ma'am,
So,
just
yeah.
ma'am, just out of the context, ma'am. This is for transpose also, right? Like if we do A
Yes.
into B. Okay.
Yes.
Okay.
Fine. So option 1 is correct. What about option 2?
False.
Why?
True.
True, ma'am. It is true.
True.
B square is P inverse AP times P inverse AP. So P inverse is identity. This part is identity, right? So you will simply get P inverse A square.
A square P.
So in fact, B power K is equal to P inverse A square A power K for any K, right? You can keep on multiplying and find it, right? This is there, right? For any K, it is true. So this option is correct. What about the next one? If
False.
A and B
That is
square
false.
is similar, then A and B are similar. Is it true?
False, ma'am.
False.
Can you give some example? This is easy. So let us say A is equal to 1, 0, 0 minus 1 and B is equal to 1, 0, 0, 1. So A square is equal to B square is equal to identity, right? So obviously A square and B square are similar, but A and B, are they similar?
No, ma'am.
No, right? Their determinant, trace, everything is different, right? So this is incorrect. Okay. What about option 4? If A and B are similar, then A transpose and
True,
B
ma'am.
true because of the similar concept here. So B transpose is equal to P inverse whole transpose A transpose P transpose. That's all. So you can rewrite this as P transpose inverse A transpose P transpose. Okay, fine.
Excuse me, ma'am.
Yes.
In the second exercise, similar matrix means a determinant not equals to 0 means are similar, ma'am.
Sorry, what?
Similar matrix means a condition is like a determinant is not equals to 0 is like a similar matrix, we can say, ma'am.
No, I never said any condition like this. B equal to P inverse AP is the condition for similar matrices.
Determinant should be non-zero now.
No, there is no such condition on determinant whether 0 or non-zero. No, determinant should be same. That's all. It can
If
be
determinant
0.
is 0, the other one should also be 0, right, ma'am?
That's all. If both the determinants should be same, that's all. It can be both can be 0 or both can be non-zero. The same value. Okay.
Okay.
Fine. Here, I guess it should be P transpose. The order I changed. So here it is P transpose, P inverse transpose. Okay. So option 4 is correct. All right. Okay. So the next concept is what are affine subspaces and affine mapping. Okay. So affine subspaces, how many of you find it very difficult to understand?
Yes, I'm finding it difficult. I can't do a model question 4.
See,
Extremely.
don't worry. See, affine spaces is something very, very simple. Okay. Why it is very simple? What are subspaces? Do you all know? If you know what are subspaces, you should be able to understand affine spaces very easily. What are subspaces? Let us start with R2. What are subspaces in R2?
Line passes through the origin, entire R2, and the zero vector.
Right? So the zero space, any straight line passing through origin, right? A whole space. These are the possible subspaces of R2. Right? Now imagine that you are just shifting that everything. It is just shifted to some other place. Then it is an affine subspace. That's all. For example, now let us say this is the origin. Now if this pointed is just shifted to another place, then this point becomes an affine space. Okay, same way, you consider the line passing through origin. If this line is shifted to some other place, it is just moved to some other place, then this one is an affine space. Same way, the R2, entire R2, if you just shift the entire R2, what will you get? You will get back the same R2 only. Nothing will get shifted if you shift the entire R2, right? Because it is the entire plane. It is again the same R2 only. R2 when shifted, it will get shifted to R2 only. So this is also an affine space. So is it difficult to understand what is an affine space? Whatever subspaces, if they are shifted, then whatever is the resultant set you are getting, that is an affine space. The same thing you can see here.
The meaning for this is clear, but not with the questions.
Okay, just hold on. Let me complete it and we will look at the definition. Okay, so here you see that point affine space means, so you see that this point A comma B, any point A comma B is an affine point affine space. And any straight line, not necessarily passing through origin, any straight line is an affine space. And the whole space R2 is an affine space. Let us look at the same scenario in R3. So first of all, what are the possible subspaces of R3? Zero space, any straight line passing through origin, any plane passing through origin, the whole vector space R3. For zero space, already we know what is the corresponding affine space. What is the corresponding affine space for zero? Any
space that is shifted. Yes.
Any point in R3, right? That is the corresponding affine space. Now for any straight line passing through origin, what is the corresponding affine space?
Any straight line.
Any line. So corresponding means we should see. For affine space, you should see corresponding. So for this line, this is an affine space. But if you are taking a different line, then this will not be an affine space corresponding to that. So we have to see corresponding to what. So if I'm taking a line passing through to origin, So the corresponding affine space is parallel to this line which you are considering.
Yes, ma'am.
Okay. Now if you are considering a plane, so any plane parallel to the existing plane is a affine space. Okay. And the entire space R3 is of course an affine space. So are you able to visualize the same in R3 as well? Yes?
Yes.
All of you? Okay. So now let us go back to the definition and see whether we are able to relate this. Okay. So now what happened in R2? Let me just quickly recall. The point 0, 0, right? So the point 0, 0, I wrote it as a comma b, some point a comma b plus 0, 0, and that became my affine space. Same way, any line, straight line passing through origin. So x comma mx, I added with the point a comma b. So a comma b, I added with x comma mx. Right? So that became my affine space. And for R2, any point a comma b added to R2, so I get back R2. So this part is your V. So this part is your V, and this is the subspace you are considering. Right? So let V be a vector space, and affine subspace V is a subset L such that there exists a V and a subspace U such that L is equal to V plus U. So what is the definition of V plus U? The set of all V plus U such that U in U. That's all. So is it coinciding with the concept we saw? Clear? Okay.
What is L related to?
The point is an affine subspace that we can write as V plus this 0 subspace. Right? So this V is your point here. Now here, suppose A comma B if I am taking. So A comma B plus this x comma mx. So this is any straight line passing through origin x comma mx. So if I'm adding a point a comma b, the entire line is just shifted to some distance, and that is now a parallel line to x comma mx. So this is your L. So this is your L. Okay. Fine. Yes or no?
Okay.
No. At least better than whatever understanding you had earlier. Okay.
Yes, ma'am.
Okay.
Yes, ma'am. We have just understood the theory part.
Okay. So now you see that this V is not unique. Okay. Why is this V not unique? Here is a proposition. So the subspace U corresponding to an affine space, here Y is not given. Maybe I will give an example maybe. So here this V is, then it will be like taking an entire session for this affine space. Let me see. I have some problems here. Just for now, let us just have this facts. Okay, otherwise it's going to take a long time. So see, there are two important things about affine space. This V is not unique, but this U is unique. Okay, this V is not unique, but this U is unique for an affine space. What does that mean? So suppose let us say you are having a line like this. Let us say this is y is equal to x. Okay, now I'm getting some other line. Let us say y is equal to x plus 1. Okay, so now for obtaining this y equal to x plus 1, I have to add some point. So which point I have to add? Which point I have to add to get y is equal to x plus 1? So I'm adding some point here, a comma b, so that this becomes x comma x plus 1. So what can be that point?
0, 1.
0 comma 1. Okay. So what if I add 1 comma 2? What if I add 1 comma 2?
Plus 1, x plus 2.
X plus 1, x plus 2. Is it still the same line?
No.
Yes, ma'am.
Yes.
Yes, right? So it means you see that this a comma b is not unique. Okay. So you are having this u is unique, but this a comma b is not unique. Are you able to see that? Yes.
Can you just explain this one again? It's not the same line. Please.
Sorry?
You just said, no, it's still the same line. Can you, okay, plus x, we have, okay, added to x comma x, right?
This is your y coordinate, right?
Correct.
This is your x coordinate.
X.
What's the relationship between them? Y is equal to x plus 1.
Okay. Got it.
Okay. Fine. Okay, so this point is not unique. Okay.
In suppose here one line y equal to x is passing through the origin. parallel to this line, any
Yes.
line, it all will be unique.
All parallel lines are affine
Unique.
spaces corresponding to this.
And
Okay.
who?
But if you are taking any line, let me complete my statement.
Sorry.
So suppose you are taking any fixed affine space.
Yeah.
Okay. Then the corresponding subspace to it is unique. Okay. For one particular affine space, the corresponding subspace is unique. For example, if you are taking this point, only the zero subspace is the corresponding space. And
Yes.
for this, particularly y is equal to x is your corresponding subspace. There cannot be any other line which is parallel to this passing through the origin, right? Only this is the line which is parallel
Okay.
to this and passing through the origin. So this is unique. Clear?
Yes. Got it. Got it.
Okay. Fine. So what is the dimension of the affine space? If L is equal to V plus U, then dimension of L is dimension of U. Clear?
Yes,
Okay.
ma'am.
Fine. So now let us do some problems. Let A be a 3 by 3 matrix and S is set of all x in R3 such that Ax is equal to 0. What is this S? S is nothing but the solutions of the homogeneous system Ax is equal to 0. Now, you see that this is some set in R3. Can you imagine what is the affine space corresponding to S? What is the affine space corresponding to S?
Null, ma'am, null space.
Already S is null space only, right? Already S is your null space.
You can choose any vector in R3.
See, you are considering Ax is equal to B. If B is equal to 0, it is a homogeneous system. And then in that case, you see that this set S is a null space. Now, if B is some vector, let us say B is some vector which is not in the column space, then Ax equal to B does not have any solution. Then this set X, so here we are considering the set of all X such that Ax. Yeah, please mute if there is some disturbance. I don't know who was it. Okay. So in that case, this set becomes empty. Now suppose B is in the column space. Then what can you see? If B is in the column space, you know that this set has some solution, right? So it means what? V is and there exists some element here, V, right? And what can you say about this V? This V, AV, and you take any element in the null space, then AV plus AU, this part becomes 0 because U is an element of the null space. So what is that? You get V plus 0. From this, you see that if V is a solution of this, then V plus U is also a solution of Ax equal to B. And this is true for any U in the null space of A, right? So it means what? The set of all solution X such that Ax is equal to B is a solution, is an affine space corresponding to this subspace. Do you understand? Here we are taking this V, where V is any element in this solution set. Do you understand what we are doing here?
Yes, we are finding a V such that Ax is equal to B, and we
Yes.
are comparing it with Ax is equal to 0.
Yes. So you see that if we are able to write L equal to V plus a null space of A, where V is an element of this, then we know that that is a affine space corresponding to this. So this is the, what is the affine space corresponding to S? This is the affine space corresponding to it. Clear? So that,
Excuse me, ma'am. Could
yes,
you please repeat it once again?
here if let us take your B to be any element in your column space of A. Then you know that there exists a solution for this. That means this set is non-empty, right? So in that case, let us take an element V in this set. Then what do you know? We know that V plus U is also an element of this set. Yes or no? Yes or no?
Yes, yes.
So this is your L. And what is this U? Your U is an element of null space of A. So this is the subspace we are considering. So this S is nothing but your null space of A, right? Okay. So we have written your L as V plus U, where U is your null space. Clear? What have we done?
Yes, ma'am.
Okay. So how we do addition and scalar multiplication on affine spaces? That is again very easy. First of all, addition and scalar multiplication, do we know how it is defined for subspaces? Yes or no? How it is defined for subspaces? Is it defined first of all for subspaces, addition and
Yes.
scalar multiplication?
Yes.
Yes, ma'am.
Yes. Then what you are going to do, you are just going to perform the addition and scalar multiplication only for the subspace part. You are going to just leave this extra vector, you are going to just keep it as it is, and you are going to perform the addition only for the subspace part. Okay. So let us take two elements from an affine space. Then you know that it has this kind of a representation. Then you are going to perform the addition only for the subspace part and going to keep this V fixed. Same you are going to do for scalar multiplication also. You are going to perform the scalar multiplication only for the subspace part and keep this V fixed. So is addition and scalar multiplication on affine spaces clear? Yeah. How to add two vectors from affine space and scalar multiplication in affine space, is it clear?
Oh, ma'am, can you please repeat once, ma'am?
See, suppose let us say I'm having this set y is equal to x is my u. Let us say this is my u, the subspace, the line passing through origin. Okay. And let us say my L is maybe y is equal to x plus 1. Okay. So now what is that? How we are going to add two elements? How are any two elements going to look like in this? Y is equal to x plus 1. How does any element in this space look like? Can you tell me? 1,
The point x plus 0.
Let us take 1, 2, 2, 3. Okay. So this is your L and this is your L dash. Right. So now L is 0, 1 plus here x, x. So 1, 1. Okay. So now same way L dash is 0, 1 plus 2, 2. So now L plus L dash is 0, 1 plus 1, 1 plus 2, 2. Is it clear?
Yes, ma'am.
Okay, same way scalar multiplication. So if I'm going to multiply minus 2 times of L, I simply have to keep this 0, 1 fixed. I'm going to multiply this minus 2 only for the U part. Clear?
So, ma'am, in this one, 0, 1 is the translatory vector, right?
Yes. In this case, I'm considering this as my V.
Okay, okay.
Clear? Okay. Fine. Okay.
And ma'am, you are considering L dash to minus 12 equal to L dash.
Sorry?
L dash is considering as minus 12 here.
L dash is 2, 3.
2, 3, but you have written here. Okay, okay.
Fine?
Okay, I understand.
Fine. Okay. See, affine mappings of affine subspaces. For now, I guess maybe we will revise it for the end term. For now, don't worry too much about this affine mappings of affine subspaces. See, what are these affine mappings? I will just tell an outline. Don't worry too much about it for now. See, let us say you have two affine subspaces and you have a function from one affine subspace to another subspace. Okay. How are we going to define this affine map? We are going to define this affine map, okay, using a linear transformation. And once you have a linear transformation, you can also define an affine map. So both this can be done. Suppose you have a function, you can define a linear transformation from this affine mapping, or if you have a linear transformation, you can define an affine mapping from this linear transformation. This is how you have to define. Okay. So only this definition, you just have a look at this. So only, and maybe for now, if you want to memorize also, you memorize what is this G, what is this F. So given an affine mapping from affine space to affine space, how to find a linear transformation to the corresponding subspaces. For that, you need this. And if you are given an transformation from the subspace to subspace, how to find an affine mapping in the corresponding affine spaces. So for
And
that,
this U prime is like translatory of U to U prime.
Yes, L is V plus U, and L dash is F of V plus U dash. Okay, so this is your L and this is your L dash. So for now, just have an idea. Just this outline is sufficient. Don't worry too much about it. What is happening inside, don't worry about it. For now, just have an outline or idea about this. Okay, fine. So now let us look at an exercise here. Let L and L dash be affine subspaces of R3, where L is this space and L dash is this space. Now for some vector spaces U and U dash, so this U and U dash are some subspaces. And what are they? U is given by this and U dash is given by this. So these are the basis vectors for U and U dash. Now how to find L and L dash? So for that, do we first of all need to find U? Do we first of all need to find U?
Yes, ma'am.
How to find U? Can you tell me?
Ma'am, if
Addition.
we give the equation, then we can easily find out. But from here,
See, U is a span of 1, 1, 0 and 1, 0, 1.
Taking alpha, beta, and solving for them, ma'am.
Exactly. So you just have to apply the definition of span. So span definition is, so you have this and this as the spanning set for U. So now what is the definition for spanning set? So alpha times of 1, 1, 0 plus beta times of 1, 0, 1 such that alpha and beta in R. So this is the definition of span of any set of vectors, right? Now how can we write it? Alpha plus beta, alpha and then beta, right?
Ma'am, x is equal to y. I'm getting a relation. X is equal to y plus z.
Exactly. So what is the relation we observe? We see that x is equal to y plus z. So rewriting, we can see that U is set of all x comma y comma z such that x minus y plus z is equal to 0. Okay. So we see that x minus y plus z is equal to 0. Now how to find a corresponding L for this? How to find a corresponding L for this?
Ma'am, x minus y minus z, no, ma'am.
Oh, yeah. So
Ma'am, we need to add
in place of z,
1, 0.
we can put x minus.
See, this we can write in several ways. This can be written in several ways. For example, maybe you can write it as maybe set of all x comma. Maybe if you put this as y, then what will be your beta? What will be your beta if I am taking this as x, y? How can you write your beta?
Alpha x minus y.
X minus y, right? So x, y, and then x minus y. So you can write it in this way or this way. So anyway, so whatever way suits for your example, that is what you have to consider. Okay. So for example, in this case, you have x here and y here. Everything is in terms of x and y. So I guess it is better to consider it in this way. Okay. So let us consider this type of a setting for this and see what is the, can you find what is the corresponding vector we need to add to get this set? So for option 1, what is your vector v which gives you L is equal to v plus u? So your u is set of all x comma y z such that satisfies this condition.
Ma'am, 0, 1, 1 I'm getting for option 1.
Yes. So you can add 0, 1, 1. So if you add plus 1, then you will get this, correct? So this is an affine space, correct?
Yes.
Okay. Yes. Now look at L dash. What is L dash? L dash is a affine space corresponding to U dash. So first of all, what is U dash then? This is very straightforward. U dash is nothing but set of all alpha, 0, 0, alpha in R. Just the x-axis.
Ma'am, without checking the options, can we do directly?
No, we cannot do. See, if you want to find any general space, then what is that you need to add? You have to simply add plus A plus B plus C, but that is kind of a very vague thing. So if you want to check what is the correct option, then you need to look at the options here. Okay.
Yes.
Fine. Okay. For L dash, now you have x comma y plus 1 comma 0. So now what is there in your y coordinate in U?
1. So option 2 is
No,
correct.
no, no. I'm asking. You have a 0
Okay,
coordinate
sorry.
here. So
Yes.
can there be a y coordinate here?
No,
If
no,
it's
ma'am.
affine space? No, right? So it cannot be affine space because there is a y coordinate here. So this option is incorrect. Do you all understand why it is incorrect? Because here if you split it, you are getting actually this set of all x comma y comma 0, which is not the scenario for us. For us, your u dash is this, not this. Right? So this option is incorrect. Now, can you tell me about option 3? What can you tell me about option 3?
Yes, ma'am, it's correct.
Okay. Now, again, why is it correct?
Since
Because
0, 1, 1 is the only vector we need to add.
0, 1,
1, 1.
But still, here you have x minus y, here y, and here x minus y. How is
Oh,
that
ma'am,
correct?
it can't be. It can't be.
It cannot be, right?
But option 4 can be, because if you put 0, 1, 1 there, it will satisfy the condition.
Yes. So here you see you have x minus y. So and when you add 0, 1, 1, the vector you are getting is x minus y, x minus y. But that is not our subspace. So option 3 is incorrect. Do you all understand why option 3 is incorrect? Yes or no?
Yes, ma'am.
Okay. Now what about option 4? So you are having 0, 1, 1 added to x, y. Is this our scenario?
No, no.
No. Again, option 4 is incorrect.
Not.
Okay.
Ma'am, but it's satisfying, na? 0, 1, 1. If you put in place of x 0.
But this is our set, not this. X, y is not our set. X, y, x minus y is our set. Right? Okay. So this is
Ma'am,
how. Yeah.
I would like to ask, what is the set of subspace U for option 3? Is it x minus y, y comma, x
Yes,
minus
yes.
y?
Yes, yes.
Okay, ma'am. Yeah.
Okay. So this is how you find the subspaces, corresponding affine subspaces for a given subspace. So far, the what is affine space and the problem we have done for affine space, is it clear? Yes?
Yes, ma'am.
Yes, ma'am.
Good. So there is one more problem. So let us now, this is the reverse case. So earlier we saw given and subspace, what is the corresponding affine space? Now we are given the affine space. See, this is very easy. I will tell you. This something you should all know. So suppose let us say for at least for straight line passing through origin in R2 and in R3 plane passing through origin, it is very straightforward. How I'm telling. In R2, suppose you have set of all x comma y such that ax plus by is equal to 0. This is a line passing through origin, correct? Yes or no?
Yes.
So now this is a subspace. What is the corresponding affine space? It is of the form set of all x comma y such that ax plus by is equal to d. That's all.
Ma'am, here you have to do one thing, that you can put in place of z, you can represent z in terms of x and y. From there you can do the operation and you will get the set.
Yes. So here for R3, the same thing, similar thing we can write. So you have to write set of all x comma y comma z such that ax plus by plus cz is equal to 0. Now what is the corresponding affine space? Can you tell me?
Ax plus by plus cz equal to some constant.
Yes. Okay. So if you have this affine space, this is the subspace, and if you have this subspace, this is the corresponding affine space. So finding this is very straightforward. So now with this understanding, can you answer this question? So L1 is this set and L2 is this set. So these are affine spaces of R3. So what are the corresponding affine space, subspaces for these affine spaces.
Ma'am, option 2 is looking like it can be,
Yes,
it can
2x
go for
plus y
L2.
plus 2z is same exactly like this, and this is 0. So this is correct. But here you see x plus y plus instead of 2 is z. So here 2 is missing. Right? So this is not correct. So option 1 is incorrect.
And option 3 is also correct.
Option 3 is true.
Option 3 is correct.
What about option 4?
Yes, ma'am.
This is not a subspace.
Not a subspace.
No. Because
this is again another affine space only.
Hmm.
Right? So this is not a subspace. What about option 5?
No.
Again, this is not a subspace. It is another affine space. Right? What about W1 intersection W2? So what is W1 is here. Sorry, W1 is here. W2 is here. What is W1 intersection W2?
Ma'am, when we do the integration, we take only common x, y, z, and the equations.
It satisfies both the equations.
Both the equation, yes.
Yes. So if it satisfies both the equation, you see that x. So let's split this equation and write it as x plus. So 2x plus y plus 2z. I can split and write as x plus x plus.
Yes, ma'am, it's satisfying.
Yeah. So now this is equal to 0. So again, we know that this is also 0. So we mean x is equal to 0 and x plus y plus 2z equal to 0. This gives you y plus 2z equal to 0. So x equal to 0, y plus 2z equal to 0. So this is correct. So all the options, are they clear to everyone? Yes?
Ma'am, can you repeat this last one once again?
Yes. See, what is happening? In W1, you have the set of all x plus y plus 2z equal to 0. In W2, you have set of all 2x plus y plus 2z equal to 0.
Okay. Y plus 2z is the common part. Okay.
Yeah. So that is why we are using both the conditions, and this is the resulting scenario.
Yeah, it's okay. Thank you.
Okay. Fine. Okay. So the next concept is dot product in Euclidean spaces. See, so far what we have seen seen that how one vector is transformed, how we are adding two vectors, how we are doing a scalar multiplication, how we are extending or shrinking a vector, and then what we saw, how one vector is transformed to another vector. So these are the things we have seen so far. So next, the important thing we should know is that what is the distance between two vectors? What is the angle between two vectors? What is the length of a vector? So these are the next question you will ask about a vector, right? So far, only the relationship between vectors like adding, scaling, and then transformation. These are the things we have seen. Now we are going to look at length, angle, okay, this kind of concepts about vectors. So that is why we are now introducing the dot product here. Okay, so now what is dot product? U dot v is u1 v1 plus u2 v2 plus etc. u1 vn. Okay, so this is the definition of dot product. And what is the length of a vector? Tell me.
Its magnitude.
u1 plus un square. Right? And you know that norm and the dot product can be related in this way. That norm of a vector is square root of u dot u, right? It is simply square root of u dot u. Right? Okay. And what is the formula for angle between two vectors? It is cos inverse of u dot v by square root of u dot u into v dot v. Okay, so this is the formula for angle between two vectors. Remember, this formula is again important. See, there are some things which you have to remember, no other option are there. So please remember this formula. Theta is cos inverse of u dot v into divided by square root of u dot u into v dot. Okay. So generalizing this dot product again. Okay, we have what is called the inner product. Whatever properties are satisfied for a dot product, these properties are summarized and we call it an inner product. What are they? So you see that we this property is called the positivity. So you see that inner product between any two vectors is always positive and 0 only for the 0 vector. And the inner product is satisfying this linearity property for the first variable, right? And then when it is symmetric, inner product u comma v is inner product v comma u. And then again, since the linearity, so that these two are linearity property. Linearity. And this one is symmetry property. And this one is positivity property. Okay, fine. So what about only in the linearity in the first variable we see? What about linearity in the second variable? Do we have linearity in the second variable as well?
Yes, ma'am. You can expand the inner product, then you can see the linearity inside it.
So using symmetry and linearity in the first variable, you can see actually the linearity in the second variable as well. So in fact, you have bilinearity. What is meant by bilinearity? Linearity in the first component as well as the second component. Okay. So remember, this linearity is not only applicable for the first component, it is also applicable for the second component as well. Okay. We are in the real space, so we have bilinearity here. Okay.
Yes, ma'am. The one kind of thing, this linearity property we have already seen in affine subspace. In the scalar multiple verification, where we are checking for u comma cv in the second part of the affine subspace, I think. We have just discussed about it.
Okay, I don't know what you are referring to, but as long as you understand, that's fine. Okay. So what is again norm of a vector? Norm is a function from V to R satisfying the following condition. So the first property is called the triangle inequality. So the first one is very famously known as triangle inequality. Okay. So the last one is this positivity again. And this is just a scalar property. So if all these conditions are satisfied by a function from V to R, then we call such a function to be a norm on the vector space. Okay. So what is the relation between norm and inner product? Just like we had relation between norm and dot product, we have relation between norm and inner product as well. The same relationship. Okay. Norm of V is square root of inner product V comma V. Okay. Fine. So consider a vector a1, b1, c1. Which of these are possible candidates for norm for a norm?
Option 1.
Option
1 and 5, ma'am.
Option 1 and 5. Okay. Why? What about the other
last option, max of mod A, B, C.
Okay. First of all, option 1, you have to verify everything. So if it's so you can verify actually it is correct only. What about option 2? Why it is not correct?
It has no meaning, ma'am. Because
So this is just B1. A1 minus B1. What does it mean? So you have a vector. So let us call this V. Your norm of V is this. But let us say you have a vector A1, B1, and let us say 1 here. Now what is norm? Let us say maybe 1, 1 here. What is the norm of this vector? What is the norm of this vector?
Root 3.
Root 3.
This is the norm definition.
Oh, by definition, it could be
0.
0. But is it possible?
No, because vectors are non-zero.
This V is non-zero and your norm V is 0. So this is not a suitable candidate for norm. What about option 3?
Option 3, ma'am, it will come as 3. But
So let us say, yeah, that is fine. But what about this very important property? What is the norm then?
A norm is
minus negative, which is not possible.
Not possible.
What about the last one?
Again, negative can be maximum,
Yes.
not possible.
So let us say -1, -1, -1. Again, norm V is -1. Right? Again, this is wrong. What about the option 5 again? What is the norm of this vector again? The same. Again, not possible. What about the last option? So this is
Possible.
option 6 actually.
Uh,
Okay, so this and this you can verify. So maybe I will.
Ma'am, in the last option, if you take the previous example -1, -1, -1, then it will give us only 1. The maximum value of the entire set is 1.
Yes. So your norm is 1. So it's
But when we are going to find out the norm of V, then it will give us root 3.
See, that is
You
what,
have
this is the definition of norm you are giving newly. That is whatever you are talking, that is called the standard norm. Okay. And this one is a different norm. Just like in vector spaces, what happens in vector spaces, the usual, we call something called the usual addition and scalar multiplication. But you know that in a vector space, addition and scalar multiplication can be defined differently, correct?
Yes, according to the
Yes,
code,
ma'am.
The
it's
same
changes.
concept here only. In a vector space, you have the usual inner product, which is the dot product, and from that you have the standard norm or the usual norm. And you can also have different inner products, which for example, you can define it in this way, or you can define it in this way, or maybe some other ways are also there. Okay, so they need not be same. The values of those norms are different. For the same vector, the usual norm gives a different value, and this norm gives a different value. All right, you understand? Yes or no?
Yes.
Okay, fine. So just make sure that you verify the properties and see whether all the properties are satisfied. It is quite a simple exercise. If you want to try, please verify. Okay. So moving to week 8, what are orthogonal vectors?
inner product is 0.
Inner product equal to 0.
So let us say you have two vectors. So we have 90 degrees. Then if you have u and v, then the inner product, dot product of these two vectors, u dot v,
0.
0. Right? So inner product u comma v should be 0. Then we call such vectors to be orthogonal. Okay. Now let us say you have two vectors which are orthogonal. It means you know that inner product a comma b is 0. Now if a plus b and a minus b are also orthogonal, what can you say about the following options? So a plus b and a minus b are orthogonal means what will you get? So let's first split this. So if you split, what will you get? A comma a plus b comma a, and then a comma minus b. So minus a comma b and minus b comma b. So now these two terms are same, right? A comma b and b comma a. So these will get cancelled.
Cancel out.
So you will simply have, this is norm a square and this is norm b square. And here this is 0. So you have norm a square equal to norm b square. So from this you have norm a equal to norm b. Right? So norm a equal to norm b you have. So option 2 is correct. But this is not the case. This need not be the scenario. Need not be. This is also wrong. This is also wrong. So only option 2 is correct here. Okay? Fine? All right. So what are orthogonal set of vectors? An orthogonal set of vectors of an inner product space V is a set of vectors whose elements are mutually orthogonal. It means what? You take this set and take any two vectors from this set, then their inner product is 0. Okay, that is
Ma'am, a small doubt. How did you define inner product in the previous case? Previous
usually
question.
what is inner product is not given to us. But we know what is the property of inner product, that's all. Only we are using the property of inner product. How it is defined is not given to us. Okay.
So in this case, we can take the standard inner product, right, ma'am?
Yes, if you want, you can take that. But it is not necessary to see what is the inner product. We have just applied the property of inner product. Okay.
Okay.
Fine. Okay. So yeah, what orthogonality implies independence. I have already explained it to you, I guess. So see, orthogonality means vectors are at 90-degree angle. So if vectors are in different directions, you already know that they are independent. So orthogonal vectors are always linearly independent. Okay. And what is an orthogonal basis? Orthogonal basis means a basis consisting of mutually orthogonal vectors. So all the elements in the basis are orthogonal. Okay, so it means that bases have that basis is linearly, that set is linearly independent. The vectors are orthogonal, right? And the dimension here is If the dimension is n, then orthogonal basis is nothing but orthogonal set of n vectors. Okay, now what is orthonormal vector? Normal set. Normal means your norm should be 1. Normal means norm is 1. So orthonormal set means it is orthogonal plus norm 1. If these two conditions are there, then we call it orthonormal. And orthonormal basis, a base is consisting of orthonormal vectors, right? Suppose let us say you have v1, v2, vn. Now this is an orthonormal basis. What is inner product vi, vj? Tell me.
0.
It is 0 for I not equal to j. And what it is when I equal to j?
1.
1. Okay. So here each vector has norm 1, right? And an orthonormal basis is a maximal orthonormal set in the inner product space. So suppose you have an orthogonal set, you simply have to divide each of the vectors by its norm to convert it into an orthonormal set. Okay, fine. So now choose the correct options from the following. Let us look at the first statement. In an orthogonal set, the norm of all the vectors are equal. Is it true?
No, ma'am.
No, ma'am.
So an orthogonal set, the norms need not be equal, right? So for example, what about 1, 0 and 2, 0? Sorry, 0, 2. They are orthogonal, but
the
the
norms
norms
are
are
different.
not equal. In an orthogonal set, the vectors are linearly independent.
Yes.
Yes.
In an orthogonal set, the vectors are linearly dependent. Of course, incorrect.
No.
If the column of an of an n by n coefficient matrix A comprises the individual vectors of an orthogonal set, then there must be a unique solution to the system Ax is equal to B. See, you have some vectors v1, v2, vn, which forms the matrix A. Now these are orthogonal. If these are orthogonal, you know that these vectors are also linearly
Independent.
linearly independent. You know that
non-invertible matrix.
Ax is equal, yes, A inverse exists. So it means Ax is equal to B.
Unique solution.
Option 4 is correct, ma'am.
Yes. So option 4 is opposite of this, so it is incorrect. And option 6, the determinant of a square matrix formed by a set of orthogonal vectors in Rn is always
Non-zero.
It should be non-zero because all are linearly independent, right? Okay. A set of n vectors can never form an orthogonal basis in Rn minus 1.
That's correct.
Correct.
True.
Yes, ma'am.
Right? Because it cannot be linearly independent.
Yes.
So why orthonormal basis? Why orthonormal basis? Because for example, we saw that suppose let us say you have a basis like this. Okay. So, okay, this is kind of becoming orthogonal. Let me take some other basis, maybe 1, 0. Okay. So now let us consider this basis. Now I'm having some maybe like 5, 11 or something like this. I want to find what is alpha and beta. How will you find alpha and beta in this case? You solve the system, right? You solve the system of linear equation. But whenever you have an orthonormal basis, you don't have to solve any system of linear equation. The coefficients are straight away found using inner product v comma. Okay, the coefficient of the first v1 is inner product v comma v1, second is v comma v2, and so on. So that is the advantage of having an orthonormal basis. Okay, so the next important concept is projections. So for projection of one vector along another vector, this is the formula.
Ma'am,
yes.
In the previous case, 1 comma 1 is not orthonormal, right, ma'am?
This is not an orthonormal basis. That's why we have to solve this system I told. But whenever we have an orthonormal basis, then we don't have to solve. That is why I gave.
Okay. Understood. Got it. Yes, ma'am.
Okay, fine. So here V is equal to inner product A comma B, divided by a comma a into a. So this is the formula for projection of a vector along another vector. Okay, don't forget this formula again. Whatever I'm putting as a box, they are important formulas. Okay, so
Yes.
just like projection of a vector onto another vector, we have a projection of a vector onto another space. So for that, this is a formula where this v1, v2, vn are orthonormal basis of that space. Okay. So let us look at the first problem. Consider an inner product. So the inner product is defined in this way. Let x is equal to 1, 2. Find the projection of x in the direction of 3, 4 using the inner product defined above. How can we do this?
Ma'am, first of all, we have to find out projection of 1, 2 with respect to 3, 4.
You have to find projection of 1, 2 in the direction of 3, 4. Yes.
Yes.
So for that, this is the formula, right? So projection of
yes, here is the form is given. Formula is given.
yeah. So this is projection of B on A, right? So it means here you see that projection of B on A is inner product A comma B, inner product A comma A times A. What is your vector? Maybe xy if you want to replace, you can write. So this x is equal to 1, 2 is your B vector. Your B vector is 1, 2. And your A vector is 3, 4. Okay. So now in place of this inner product, you have to use this formula and substitute this. Shall we do this problem?
I think it's better to skip it, ma'am, because
Yes,
it's not.
yes, this
It's
is kind of
very big.
yes, this is kind of a lengthy one. I just want.
Ma'am, I have solved already the question. So it is coming as 25 by 49, 3, 4.
I am not sure about the solution, but it is there in the book. That book is there, right? Where you have the linear algebra book prepared by the instructors. So that book solution is there, I guess. Please check that.
Ma'am, this is also part of the activity question.
Then I guess you can find the solution there. Please check that there. I don't want to solve this one.
But ma'am, the second part solution, I think, just let me open the book.
Okay, please check the book. If you have doubts, we can discuss. Okay. Okay, so this is a lengthy one, so I'm skipping.
Ma'am, second part solution isn't given.
Second part solution is not given.
No.
Okay, so let x is equal to 1, 2. Find the projection of x in the direction perpendicular to 3, 4. What is the direction perpendicular to 3, 4? It is very simple only. What is
We have to take dot product. Sorry.
Equal to 0.
Inner product.
Ma'am, it will be the
equal to 0.
inner product.
You have to take inner product x, y, 3, 4 equal to 0. Apply this formula and find what is the x, y by solving the equation. That's all. Okay, that will give you the vector A. So this is your vector A. Here you need to find what is your A. Okay, by applying this formula here, you just have to solve it and find it. Okay. You understand what is it you need to do? X is perpendicular to 3, 4.
After finding x and y, we need to project B on x and y. Right? Is that the way, right, ma'am?
Exactly.
Okay.
Fine. If you want, maybe I can tell the TAs to solve this question specifically tomorrow. Okay.
Yes, ma'am.
Okay, I will tell the TAs to solve this one tomorrow. Okay. So these properties, whatever we are going to discuss here, are really important. So here, projection as a linear transformation. See, this projection map defines a linear transformation. Okay. So for a linear transformation, we know that there is a range, there is a null space. So correspondingly, the dimensions are there. So for this particular projection map, what is the range of T? What is the range of any projection map?
W.
W. What is the rank of the projection? The
Rank of
dimension
V.
W. What is the kernel of T?
Dimension W per.
Kernel.
Sorry,
Nullity.
Sorry.
Nullity of V.
W perp, right?
It is just
Or
W perp. But
W
what is
perp.
W perp? W perp is the set of
Orthogonal
vectors orthogonal to all vectors from W.
W.
Okay. So orthogonal complement is the set of all vectors orthogonal to all vectors of W. Right? Fine. So what are the other properties of projection operator? P square is P. So if P is a projection operator, then P square is equal to P. Right? And what about the, see, for example, look at this picture. So see, sometimes some pictures should be there in your mind for immediate visualization. So look at this vector. This is projected onto this vector. Okay. So now this is the original vector. This is the projected vector. Which one has bigger norm? The original vector or the projected vector? Which one has bigger length?
original vector.
Original vector, right? So this is a general property for any projection operation. So the norm of the projected vector is always less than or equal to the norm of the original vector. Okay, so that projection cannot be longer than the vector itself. Okay, and if you apply rank nullity theorem, here what will you get? What is rank nullity theorem? Rank of PW plus nullity of PW is equal to dimension of V. Now, what is rank of PW? It is nothing but dimension of W, and nullity of PW.
Or image also, right, ma'am?
Yeah.
Dimension
Sorry.
W per.
Yeah, it's dimension of W per is equal to dimension of. Okay, fine. Let V be the plane spanned by the vectors V1 and V2. V1 is 1, 1, 0. V2 is 0, 0, 1, 1. How do you find V perp? See, if it is just one vector, it is very easy. You just put, suppose for example, only one V1 is given. Then what will you do? You take a vector x, y, z, do the dot product with 1, 1, 0. What is it you will get? X plus y is equal to 0. Only this you will get. Now you have one more equation, that's all. So now this x plus y plus, sorry, x comma y comma z is also orthogonal to 0 comma 1 comma 1. Okay, so you see that here
Y
now
plus
y
Z.
plus z is 0. So here it means what? Your x plus y is 0, y plus z is 0. So here y is equal to minus x, your y is equal to minus z. So it means what? Your x is equal to z. Correct?
Yes, ma'am.
So it means your V perp is the set of all vectors x comma y comma x comma y in R. So randomly take one vector from here. For example, let us take 1, 0, 1. Okay, if you take 1, 0, 1, but hold on, did I make any mistake? Yes, I have made a mistake. How I am saying I made a mistake? Can you tell me? What is the dimension of this space which I have written here?
2, ma'am.
Can it be 2? Can it be 2?
Yes, because you are 2 times.
No, it cannot be 2 because
Only
dimension of
3.
V equal to 2. Dimension of V perp should be 1, right?
One.
Sorry.
Yeah.
Yes.
Yeah, okay,
So
yeah.
whatever I have written is incorrect because you have to write y as minus x.
Okay. Dimension is 1 basically.
Yes. So the dimension is 1.
Ma'am, one step behind. I could the rank nullity theorem once again. Could you just go back? Yeah, there. Not the concept. In the question, ma'am.
Here.
Yes, ma'am. Yeah. Once could you
So,
repeat? How did you just make that statement?
see here, because of the rank nullity theorem, I know that your the whole space here is R3. Okay, and V is the subspace of R3. So if V has dimension 2, then dimension of V perp is 3 minus dimension of V. So it should be 1. Okay,
Yes,
from
ma'am.
rank nullity theorem. So that is why I know that whatever I wrote earlier was wrong. So I checked again and saw that it is, of course, one-dimensional space, and any vector is of this form.
Yes, ma'am. Ma'am, dimension of V is to you have considered by V1 and V2, right?
Yes, of course, because
Oh,
we
okay. Yes, ma'am. Done.
this spanning set, right?
Yes, ma'am. I understood. Yeah, got it. Clear.
Yeah.
Ma'am, so this 1 comma minus 1 1 is the span of the null space, right? Basically, basis of the.
We have not considered any projection here. We are just considering a
Okay,
set
okay,
and
okay.
orthogonal complement.
Okay, okay, got it, got it.
Okay, now you can easily check one. Let us call this V3 maybe. What is V1 dot V3?
0.
0. 1 minus 1, 0. Again, what is V2 dot V3?
0, ma'am.
Minus 1 plus 1, 0 again. Okay, you can easily verify. Okay.
Request ma'am, V perpendicular depends on the dimension what we get.
Yes, suppose B has dimension 1, then V perp will have dimension 2.
Okay.
Fine?
Yes.
Okay. Now you see that in R2, you are
Sorry
having.
to interrupt.
Yes.
Ma'am, so in the above question, say for example, if we had only one vector v1, right, in this one. So in this case, dimension v per would have been 2, right?
Exactly. So for example, let us say you have some vector v is equal to, let us say 1, 2, 3.
Correct.
And let us say your u is span of this v.
Correct.
What is u perp? U perp is set of all x, y, z such that x plus 2y plus 3z equal to 0. And this is the equation of a plane. So the dimension is 2 and here the dimension is 1, correct?
Correct, correct.
Okay. Okay. So now W1 is set of all x, y such that y is equal to 2x. And W2 is set of all x, y such that y is equal to minus 2x. So we need to find the orthogonal complements. How are we going to find the orthogonal complements? So here this inner product is defined differently. Please, no, the usual inner product only. So with the usual inner product, it is very easy, right? So take a basis for W1, then you can easily find. What is the basis for W1? If x is equal to 1, your y is going to be?
2.
2.
1 comma 2 is the basis.
Yes. So you can take 1, 2. So what is the vector which is orthogonal to this? X plus 2y equal to 0.
Yes.
So it means 2y is equal to
X minus x.
minus x. Right? So this is for W1. And for W2, what is the basis? 1 comma
minus 2.
minus 2. So when you do the dot product,
X minus 2y is equal to 0.
so 2y is equal to x.
Minus x.
2y equal to x, right?
Okay.
So which options are correct? This is incorrect. This is incorrect. This is correct. This is correct. Right?
Yes, ma'am.
Okay. So
Excuse me, ma'am.
Yes.
Ma'am, in case if we have a full dimension for W1, it's 2, then is it possible to find orthogonal component for that?
Of course, very easy. What is orthogonal complement? Tell me the answer.
0.
Yes. Only the zero space.
Ma'am, I just gave a guess. Ma'am, I couldn't listen to the question. Could you repeat the question of her question?
Yes. See, her question was that suppose your W is entire R2. What is W per? This was her question. Okay. So
With respect to R2 only she asked, right?
Yes. With respect
Okay,
to
yeah.
With
Got
respect to R2, it should be R, no?
Sorry?
It should be R because dimension of W is 2.
Yes, so here you are considering W as a subspace of R2 only. So you are considering the entire space as your subspace. So what is the orthogonal complement of the entire subspace? Apply again orthogonal rationality theorem. This dimension should be 0. So what is the space which has dimension 0?
Null space
Why
of
its dimension should be 0?
Only the 0.
0.
Only the
Sorry,
0.
0. Yeah.
Okay. Fine.
Ma'am, by this logic, if we have the n space with full rank or full dimension, In that case, the 0 vector will be always a orthogonal vector for any.
Here the null space is the full rank of the matrix.
If W is your entire space, then W perp is always the zero space. And if W is your zero space, your W perp is definitely the entire space. Fine?
Okay, ma'am. Yeah.
Okay. Fine. So, yeah. Choose a set of correct options. Suppose beta is equal to V1, V2, Vn is an orthogonal basis of an inner product space. If there exists some V in V such that V is perpendicular to each of this, orthogonal to each of these vectors in the basis. What does that mean first of all? If V is orthogonal to each of this vector, does it mean that V is orthogonal to all the vectors in the whole space?
No, ma'am. Then beta will not remain a basis.
No. You are.
Ma'am, it is. Ma'am, could you repeat? I got confused. I guess it's right.
See, my question was that suppose you have this condition. Does it imply that inner product V comma U equal to 0 for all U in V?
Yes.
Yes, right?
Yes.
Why is that so? Because you know that your U is summation alpha I Vi. And what is inner product V comma U then? Summation alpha I into inner product V comma Vi. And V comma Vi is already 0. So this is 0, right? Got it? Yes or no?
Yes, ma'am. Yes,
Okay.
ma'am.
Okay. So
No, ma'am.
what is that you don't understand? See, if Vi form a basis. If it forms a basis, you know that any vector can be written as a linear combination of the basis element. That's why this representation.
Yes.
So apply this representation here. Apply the linearity property and bring the scalar outside. Then use this property here. Then you see the product V comma U is 0.
Okay. Okay. Yeah.
Okay. So it means what? V is a vector which is there in capital V perp. Now, V is your entire space. What is your V perp then? Just now I told you, if you have the entire space, what is orthogonal complement?
0.
So what should be your V then?
Entire space.
What should be the small v?
0 vector.
It's 0.
Yeah.
Ma'am,
Capital V, small v is kind of confusing. Okay. So the small v should be 0. You understand? Because the small v belongs to just the singleton 0 set. So your v is 0. Clear?
ma'am, there is a small doubt, ma'am.
Yeah.
Ma'am, when we say inner products of V comma Vi, then V is individually multiplied with all the components of Vi.
Yes.
We can say. Ma'am, there would be a certain place where we will get V itself in Vi, because it is part of that.
Exactly.
Then that
Exactly.
inner product won't be 0, na, ma'am.
See, that is why. See, that is what is exactly happening. That is what. See, inner product V comma U is 0 for all U in V. Correct? Do you see this statement? This statement you understand?
Yes, ma'am.
So it means in particular it is true for U is equal to V as well. Yes or no?
Okay, then V is itself 0.
Yes, that is what is the statement. This means V is 0.
Okay, ma'am. Now I'm getting it.
Yes, you can see this in multiple ways.
Then
Okay.
V.
Clear? Okay.
Ma'am, if V is not equal to 0, then it should be 1, right? Like V inner product would be 1, right?
It will be norm of.
With the norm.
So square of norm of
V square.
Question.
Yes, ma'am. Okay. If it's an orthonormal basis, then it would be 1.
Yes.
Still
Okay, yeah, I understood. I got it, ma'am. No problem.
Okay. So option 2, there exists an orthonormal basis for Rn with a standard inner product. True or false?
True.
True. Always there is a standard with respect to standard inner product. You know that the standard basis is always there, right? Okay. So if PW is a linear transformation which projects the vectors of an inner product space to a subspace W, range of P intersection null space of P is 0. What is range of P?
W.
What is null space of P?
W perp.
So what is the intersection in these two? What is there in W as well as W perp?
0 vector.
0.
So obviously this is correct, right?
Ma'am didn't get the statement itself, ma'am.
Yeah, that is kind of a statement only. What about the last one? 1 minus 1 0 1 cannot represent a matrix corresponding to some projection. What is the property for any matrix representing a projection operation? What is the property?
A square is equal to A.
Exactly. So from this you know that the corresponding matrix will have this property, right? So does this matrix satisfy the property? Check it. What is 1 minus 1 0 1 square? So you have first place it is 1 and then here you have minus 1 minus 1 minus 2. It is changing. So
it's not same.
2. Yes, the same matrix. So let us call this A. So A square is not equal to A. Okay. So this is correct. This cannot represent a projection. Clear? All the 4 options are clear for everyone? Okay. So the next one is Gram-Schmidt process. What is this Gram-Schmidt process? Given any basis, how to convert it into an orthonormal basis. So here you have a series of steps here. What is one thing you should notice here? What is this? Can you tell me?
Projection of V2 on U1.
Projection of B2 on U1. Okay. So same way you see that this becomes a projection of V3 on the span of U1 U2. Okay. So like this you can see each of this particular part is the projection of Vn on span of U1 U2 Un minus 1. Okay, that is something you should note. Okay, fine. So yeah, any finite dimensional inner product space has an orthonormal basis. And yeah, the next important topic is what are orthogonal transformation. Again, this is very important. So what are orthogonal transformations? Orthogonal transformation is a transformation which satisfies this condition that inner product T comma V comma T comma W is equal to inner product V comma W. Right? It means what? It preserves length and angle. What does it mean by preserving length and angle? What does it mean?
The length and angles don't change if we performed orthogonal transformation.
Exactly. Suppose, for example, you have a vector 1, 2, 3. What is the length of this vector?
Under root
14. Root 14. 14.
Root 14.
1 plus 4 plus 9, root 14. So let us say you have a orthogonal transformation. Now, what is the norm of T of 1, 2, 3?
It has to be 14 for orthogonal.
It is again square root of 14, right? Because orthogonal transformation preserves length. So it is exactly same as norm of 1, 2, 3. Correct? You understand?
Ma'am, but if both length and angles are preserved, then basically we are not doing anything.
No. The positions can shift.
Right? Oh, okay. Yes.
Yeah. Okay. Orthogonal transformation preserves length, we saw. Now, how to see orthogonal transformation preserves angles? So, let us say you have two vectors. Okay, how do you find angle between two vectors?
Dot product.
Cos inverse of
V dot inner product of VU divided by norm of V norm of U.
Yeah, square root of U dot U V dot U. Right? So now suppose you have u and v given to you. You are asked to find the, suppose you have a orthogonal transformation. What is the angle between tu and tv?
It will be same.
It's the same, right? The same theta. So if you are asked to find the norm of a transformed vector, it is the same as the norm of the vector. Again, angle between the transformed vectors, it is the same as the angle between the original vectors. That is the meaning of orthogonal transformation preserves length and angle. Okay. So now what are the important properties of their matrix representation? So let us say A is a matrix representation of an orthogonal transformation. What are the properties it satisfies? It satisfies this property that AA transpose equal to A transpose A equal to I. So a matrix satisfying this property has some other name. What is that?
This is a standard form of matrix.
What is the definition of inverse of a matrix?
Adjoint A by determinant of.
No. Definition, you are giving the formula to compute. I am asking the definition. A matrix which satisfies this property is called the inverse, right?
Yes.
So it means what? Here, if it is an orthogonal matrix, you know that your A inverse is simply A transpose. You don't have to do any computations for finding the inverse. Inverse is simply the transpose of the matrix. This is an advantage for orthogonal matrices. You simply have to compute the inverse of the transformation. Clear? Yes? Okay. So one thing you note that if only this condition is there, then only the rows are orthonormal. And this condition implies that the columns are orthonormal. Only when both the conditions are there, you can say that the columns as well as the rows are orthonormal. It means what? For an orthogonal matrix, the rows as well as the columns form an orthonormal set. Is that clear? Yeah. So for an orthogonal matrix, the rows and columns are orthogonal. So from that, you can actually, if you are given a matrix like this, okay. So let us see this matrix. Look at the rows. Are they orthogonal? So you have these rows. Let us call these rows to be R1, R2, R3. What is R1 dot R2?
Minus 1 by 2.
No, it's not 0.
It's not 0. Minus 1 by 2.
Minus 1 by 6.
1 by 6.
1 by 6.
And then plus 1 by 3. What it is?
It will be 0.
Yeah, it is 0.
0, right? Same way R1, R2 dot R3.
R2 dot R3 will be 0.
0. R1 dot R3.
Same, it's also 0.
See, so you have this condition that A transpose equal to identity. Now, what about what about the columns C1, C2, C3? What is C1 dot C2? 0, right?
0.
C1 dot C3?
Again 0.
What is C2 dot C3?
0.
Right? So again,
Columns and row both are orthogonal.
So it means this matrix is an orthogonal matrix.
Ma'am, if the rows are orthogonal, but the columns are not.
That is possible. So then it cannot be an orthogonal matrix.
So ma'am, for orthogonal matrix, ma'am, so both these conditions are needed, right? A transpose equal to A
Both the
into H.
conditions are needed.
Okay.
Okay.
Ma'am,
So now,
suppose the rows are orthogonal and columns are orthonormal.
Then also it is not possible. See, if they are just orthogonal, you won't get an identity matrix. You will get some diagonal matrix.
Normals should be also orthogonal, right?
Yes. The other way around is true. So now
Ma'am.
let's look at the options.
Ma'am, just a simple question, ma'am. Why do we need this orthogonality property, ma'am? Over
Why?
here in this matrix.
Oh, the question is checking whether this matrix is representing orthogonal transformation. That's why. Sorry, I did not let you to look at the options. Okay, did I answer your question?
No, ma'am. My doubt is we have this transformation matrix and we are checking whether the rows are orthogonal to each other, and similarly we are checking for columns are orthogonal to each other or not. But why are we doing this? That's the question.
Because I want to check whether this matrix is representing a matrix of an orthogonal transformation. If it is representing a matrix of an orthogonal transformation, it satisfies this condition that the rows are orthogonal and columns are orthogonal. That's why I'm checking it. Okay.
Ma'am,
So for orthonormal, norms also should be determined, right?
Norm of each vector should yes, norms of each vector also should be 1.
So that here it is orthonormal rows and columns or orthogonal. We have checked only orthogonal, right?
Here only orthogonal is there, normality is not there. Please check. It is there. They are all normal vectors.
Ma'am, how row in the case of row vectors, could you just check normality? I'm not able to get norm as 1 for rows.
Rows, it is not satisfying. Let us see.
I feel.
Okay, I did not check it. I assumed it kind of. So 1 by 2 plus 1 by 6 plus 1 by 3. What is the norm?
1.
What's the problem here?
Minus 1 by 2, right, ma'am? Rows, right?
Yeah. So I'm just squaring each of these entries.
Ma'am, no, you're writing 1 by 2, right? Instead of
It has to be minus 1 by 2.
Minus 1 by 2, na, ma'am?
First
one, ma'am.
Yes.
1 by 2 will be minus 1 by 2.
Minus 1 by 2, na, ma'am?
No, squaring.
Minus 1 by 2.
Squaring 1 by 2. Okay, can norm.
1 by 2.
We are finding the norm, not the length of. Okay, got it.
Yeah,
okay.
It's fine. It's fine.
Yeah.
Okay. So here you see that because it satisfies this condition, T is an orthogonal transformation. Okay. So T is an orthogonal transformation. So this is incorrect. Now B is a real symmetric matrix. Is that true? Yes or no?
Ma'am.
Yes, ma'am. True.
Yes, ma'am.
Someone is asking a doubt, I guess.
Yes, ma'am. Can you explain the option 1 again, ma'am, once?
See, U is an orthogonal matrix.
Correct.
If U is an orthogonal matrix, the corresponding transformation is an orthogonal transformation.
Ma'am, it is an orthonormal matrix, right?
See, the name is kind of confusing. See, the definition is like this. A matrix representing an orthogonal transformation. So this is also, we are calling only orthogonal transformation, not orthonormal transformation. And the matrix representation is also called orthogonal. But it satisfies the property that they are orthonormal. The name is kind of confusing, but this is the...
Ma'am, I'm having a confirmation. So the rows and columns, if they are orthonormal, then the matrix is called as orthogonal matrix.
Exactly.
That implies orthogonal transformations.
Exactly.
Thank you.
So, ma'am, basically we are checking for the length here, right? If it is 1 or not.
We are checking for the length as well as orthogonality. We are checking orthogonality as well as normality.
Understood.
Okay, fine. So B is a real symmetric matrix, true. Now for option 4, we need to find U inverse. So how to calculate U inverse? Can you tell me?
Transpose.
Just use a transpose. Okay. So now you have to calculate what is U transpose BU. So I don't want to do the calculation. So I will leave it as a homework to you. So what is the homework here? So you have to calculate what is U inverse BU. So it is nothing but U transpose BU and see which one is a suitable option. Okay.
Ma'am, U transpose U will come as identity matrix. So answer will be B.
U transpose U is identity, but we are not computing U transpose U. We are computing U transpose BU. Okay. So compute it and complete this problem.
Ma'am, what was his question, ma'am?
He said that U transpose U is identity, so this should be a diagonal matrix, he said.
Matrix doesn't follow commutativity. Matrix multiplication.
Commutative. You have to go in that order.
Okay. So complete this by calculating this. Okay. One last question is here. So you have a system of linear equation. A be the coefficient matrix of the above system of linear equation. Which of the following is true for the matrix A transpose? Okay, so let us write what is your matrix A. 1 minus 2, 3, 2, 1, 0, 3, minus 6, minus 5. So minus 2 plus 2, minus 3. Are they orthogonal? No, right?
Yes, ma'am, they are orthogonal, ma'am.
They're orthogonal.
Yes, ma'am, they are orthogonal.
No, orthogonal, ma'am. Rows are orthogonal to each other, ma'am.
Okay, rows are orthogonal to each other. Okay, fine. So I'm looking at the column. Okay, we have for A transpose, we have to look at the rows, correct? So we have considering R1, R2, R3. So then 2 minus 2 is 0, 3, and then plus 12 minus 15 is 0, and then 6 minus 6 is 0. Yes, rows are orthogonal. So if rows are orthogonal, what do we know?
A transpose is IA.
You see that A transpose, if it is orthonormal, it is identity. If they are orthogonal, what will we get? Can you tell me?
Length of that.
See, suppose we are having 3 vectors. Okay, so V1, Vi, Vj is 0 if I not equal to j for orthogonal set. For orthonormality, we have 1. So for any orthogonal set, what is Vi?
Length square. I mean.
Yeah, it is some number, right? Some number, right? So this is some number. So it means we should get actually a diagonal matrix, correct? Yes or no?
Yes.
Yeah.
Yes,
So what
ma'am.
is the norm of each vector? You just calculate it and see whether they are different or same. If they are, definitely it is a diagonal matrix. It is not the identity matrix. But is it a scalar matrix? That you should compute the norm and check. The norm of first vector and second vector are obviously different, so it cannot be a scalar matrix. Correct? Yes or no?
Yes, ma'am.
So is it a lower triangular matrix?
Yes,
Yeah,
ma'am.
ma'am.
Since it's
Yes,
a
it has to
diagonal
be.
matrix, then
Yeah,
both options.
Okay, fine. Okay.
Yes, ma'am.
Okay, so there is one point which I have not covered. So I'll ask you this question, you try to answer. What is the determinant of an orthogonal matrix?
It has to be
Non-zero. Non-zero.
Okay,
Plus or minus 1.
Why plus or minus 1?
Because A into A transport, determinant of A and determinant A transport, you can tell that a determinant square equal to 1, and the square root will go to that place, and plus or minus 1. Yeah.
So determinant of A transpose is same as determinant of A square, and that is same as determinant of I, which is 1. So determinant of A square is 1, implies determinant of A is plus or minus 1. Okay. So that's all. We have covered all the topics. I hope the session was useful for you.
Can you take a question and
Bro, I'm having a small doubt regarding dimension. Sorry, basis, ma'am.
Yes.
Like I'm having a difficulty in if there is an subspace given, getting the basis for subspace. I'm having a difficulty. I'm having 2 cases. Could you just solve it for me, ma'am?
What kind of scenario you have?
If
Like
yes, ma'am, some sort of like that. But I'll give you 2 cases. Like it's similar to that, but yeah. If x1 plus x2 plus x3 equal to 3, then what is the basis? Could you just get it for me?
Is it first of all a subspace?
No, because 0 is not there.
Yes, it's not a subspace.
Oh.
Okay.
Ma'am, sorry to interrupt. When we get this PDF back to
Right after the session, you will get it.
Okay, ma'am. Thank you.
Ma'am, sorry to interrupt you.
Yes.
I just want to have, ma'am, Gram-Schmidt, ma'am, can you repeat it once again, ma'am? Gram-Schmidt for converting
Gram-Schmidt is basically a set of formulas only. There is nothing much to explain. That's why I did not spend much time there. You have to kind of remember that formula. Yeah. So if you are given a set of vectors v1, v2, vn, which is forming a basis, then to convert it into an orthonormal basis, So first you just divide it by its norm for the first vector, and for the second vector you apply this formula. Okay, v2 minus projection of v2 on u1. Same way you keep on applying for each of this vectors till you get an entire basis of orthonormal vectors. So this is just some formulas, that's all. Okay.
And in the end, we will get the U1, U2, U3, ma'am, isn't it, ma'am?
Yes, and in every step you are getting U1, U2, U3, and that finally this U1, U2, U3, that gives you a orthonormal basis.
Fine,
okay.
Thank you.
Yeah. Any other questions?
Ma'am, I am getting confused in 1 and N2 mapping of linear transformation.
1, 1 on 2, what kind of confusion?
Means, suppose there is a vector space is given, and from there a linear transformation is also defined. They are asking for that. Is the linear transformation is on 1, 1 or on 2 or both?
Sorry, your voice is breaking.
Now it's clear.
Yes.
So
I
they are giving a vector space. It is represented as a matrix, a 2 cross 2 matrix, and from which is a linear transformation is defined from the vector space to R3. And the linear transformation is also, after that the transformation is also defined. Based on this information, we have to say that the transformation is 1, 1 or on 2 or both.
What is your V?
V is x minus x, y minus y.
Okay, matrix form.
Matrix form.
Okay. Okay. So I guess I understand the scenario. This is from V to R2, right?
V to R3.
R3. Okay.
And the transformation is also defined.
Okay. So one thing I can tell you, definitely this cannot be both 1 to 1 and on 2. Can you see it straight away? It cannot be definitely both 1 to 1 and on 2. Both the conditions cannot be possible together. Is that clear to you?
Yes, ma'am. Here we can easily say that it is not on 2 because the dimension of the vector space and the R3 isn't same. It's not equal.
Yes.
But how can you define it? It is 1, 1.
That you have to check depending on the transformation. You have to check that.
The transformation is given as the key of the same matrix will be x comma y comma x plus y.
X comma y.
X comma y comma
This
x
one,
plus
right?
y.
Yeah. So now suppose t of x comma y comma minus y.
Is x minus x, ma'am. I think there's a typo. X minus x, y minus y.
Yes, x minus x.
So you have to check whether this space, so this is 0 means, does it imply both x equal to y equal to 0? So definitely you see that if this is 0, it means that your x comma y comma x plus y is 0, 0, 0. So your x is 0, y is 0. So if x is 0, y is 0, this vector is, this matrix is the 0 matrix. So it is 1 to 1. That's all. Your null space is just a 0 space. Here?
And how can we check for onto, if you don't mind?
You tell me how to check onto here. What is the dimension of your domain and what is the dimension of codomain?
Okay, okay. Got it, got it.
Okay.
Ma'am, so from here you are defining the x equal to 0, y equal to 0.
Yes, it means your matrix, so you have TV equal to 0, implying V equal to 0. It means T is 1 to 1, right?
Yes.
Got it?
Got it.
Okay.
Ma'am, regarding affine mapping, ma'am, suppose if there is f of x comma y, can you please write it, ma'am?
Okay, affine mapping you want to do? Okay.
F of x comma y is equal to ax plus by plus c, comma mx plus ny plus r.
Okay, I guess I remember this problem. Can you just write this question maybe in your I don't know
Ma'am,
what is
it's
it
not
called?
it's not a problem, ma'am. I'm asking whether any affine space can be represented in this manner. Ax plus
Affine space or affine
sorry,
map?
affine map with f of x comma y is equal to, can it be if there are only two outputs, like if the output is always in R2, it has to be represented in such a manner, no ma'am? Ax plus by plus c comma mx plus ny plus r. Is that a correct statement?
Okay, I understand what you're asking. Just like we have a representation for any linear transformation,
Correct, ma'am. Yes, ma'am.
we have a representation for an affine map.
Yes, ma'am. Yes, ma'am. Exactly, ma'am.
See, affine maps again, they are mapped to affine space. So affine spaces have some specific way of representation, right?
Okay.
So affine space is how are we defining again? It is a vector plus a subspace.
Right.
So here that is what you are actually trying to do. You are kind of trying to write c comma r plus ax plus by comma mx plus ny. This is something like that you are trying to do.
Right.
Yes, it is more or less correct, I guess. But I have to verify whether your statement is correct. I feel that it is correct, but anyway,
Yeah,
I have to.
intuitively it is correct to me as well, ma'am.
Yes,
But
yes,
I just
it
wanted
looks
to make
correct.
sure.
It looks correct only, but I have to verify and tell you. I'll check and
Sure,
let you
ma'am.
know.
No problem. Ma'am, one more question. Affine mapping. Our lecturer in the lecture, professor told that t dash. Suppose t is mapped from v to w, and t dash is mapped from v to w as well. So t is a linear transformation and t dash is an affine transformation. Then we can write t dash of v equal to w plus t of v. So can you once, so
You are asking me to explain this part.
yes, ma'am. I want you to explain this part. And there's an example also in one of the tutorials. X comma 1 is going to x comma x plus 1. Can you write this in that form and explain it once well? Can you make it like a
Ma'am, just one thing.
Okay, let me just tell one
Definition.
thing to him. One thing to him, and then I'll move on. See, whatever this doubt you are asking, either put it in discourse or maybe you specifically write it. I guess putting it discourse is better so that others also will get to understand this part. Maybe you can refer to the video link and the time where you are asking that part.
Ma'am,
So
day after tomorrow is the exam, no, ma'am. Could you please give a quick explanation, if possible?
see, I have to look what is that explanation given there, and I have to explain. Just you are explaining
Ma'am,
it. I'm not able to visualize.
no, it's just
Hold
3 lines, ma'am.
on,
It's just
hold
3
on,
lines.
hold on. Let me complete my statement. So put it
Sure,
in
ma'am.
discourse today. Tomorrow, if possible, I will explain in the TA session, or I will tell the TAs to explain in the TA session.
Sure,
Okay?
ma'am. No problem.
Ma'am,
Ma'am, but
Put it in the
this
discourse.
one x comma 1 is going to x comma x plus 1. Can you just tell that at least? Just that small.
X
How will
comma
you
1.
is going to x comma x plus 1.
Okay.
How will you break this down into a linear map plus affine? How to show that it's an affine map?
So what is the space behind this? So this is the space you are
X comma
considering.
0.
So, okay.
X
So you
comma
are.
0 and x comma x.
So this is your affine space, and here you are having 0 comma 1 plus x comma x. So what is
Right.
the map? What is the map? You have just given me the domain and codomain. What is the map?
This is the map. Codomain is codomain is r square, and domain is also r square.
I don't understand what is your
R to R, ma'am. Domain and codomain. How to
R. R2 to R means you should explain
R2
it
to
for
R2, ma'am. R2 to R2. R2 to R2.
R2 to R. This map is not from R2 to R2. You are just given the domain as L only. This is your domain.
Right.
Way you have given, this is your domain.
Sorry, ma'am. Sorry, my bad. The domain is not R2. Domain is x comma 1 only. Sorry, sir.
Okay. And this is
And
your codomain.
yes, codomain is also that. Yes, ma'am.
So what is your map?
That is my question, ma'am. How will you map, like tell
See,
them
I
that?
don't see whatever page from wherever you are referring, please maybe take a screenshot and put so that I will also have a clear understanding to answer. Okay,
Okay,
please.
ma'am. Sure, ma'am.
Yeah.
Ma'am,
Yes.
ma'am, just needed two small confirmations. Ma'am, so
Yes.
ma'am, if we can say that, ma'am, the dimension of the codomain is basically equal to dimension of the range space. So in that case, it's onto, right?
Exactly.
And ma'am, for one dimension of domain has to be equal to dimension of the range, right?
For 1 1.
Yes.
No. For 1 to 1, you just have condition on the null space. The null space should be 0.
T of v equal to 0 for v equal to 0. That's it. Like we'll have to check it, right? For the null space, basically.
Yeah, null space should be 0. That is what you need to check. For onto, you need to check the range, and for 1 to 1, you have to check the null space.
Okay, for onto we can check the dimension of the range and the codomain, and for 1 we can simply check this first. This
Yes.
T
Yes.
of the transformation 0 is equal to 0 or not, basically.
Yes.
Okay.
Okay.
And because actually I think we had a like in one of the sessions it was told that like if dimension of the this thing like range is equal to dimension of the domain, probably then also it's something like that it was mentioned.
Okay, so I guess this is the scenario you are talking, I assume. So if T is both 1 to 1 and onto, then we have this implication that dimension of domain is equal to dimension of codomain.
Yes, ma'am.
This implication is there, but converse is not true.
Dimension of domain is equal to dimension of codomain. Okay.
If both 1 to 1 and onto, then we have this condition.
But for 1 we can check that only, right? Tx comma y equal to 0
Yes,
for x equal to 0, y equal to 0. Okay.
Ma'am, one more small clarification, ma'am. T of u is equal to f of u plus v minus f of v in affine transformation. Could you just explain that, ma'am? I did not understand that, ma'am.
This one?
Yes, ma'am. Exactly that, ma'am.
You are asking me to teach affine transformations. Huh? So
No, ma'am. I didn't understand how that specific function. Could you just give a briefly cover it?
See, I have to see without explaining this, I cannot explain this. Both are kind of interlinked part only. From here only I can come here, and this is kind of interlinked part. One thing I will do, I don't remember whether I taught this topic for this term or not. I don't remember. I don't think I have taught this, right? For this term. Otherwise, I can just refer you to the lecture. No, right?
No, ma'am.
Then I will do one thing. I have taught it for some of the previous term. Maybe I will check for which video is there where I have taught it, and I just refer it to you. I have explained it completely in the lecture video. Okay, so I can refer it to you there. So I will give you the link of that video to you. Okay, maybe I will put it in the Google Sheet, maybe near
this portion explanation.
Yes, I have explained this completely in one of the previous terms lecture.
Okay. Ma'am, so G of u is equal to f of v. Ma'am, f is acting on just the constant term that is being added, right? If I'm correct.
See, it is not at all constant. It is a vector, fixed vector.
Fixed vector. That's what I mean. Yes.
Yeah. Okay. So here the domain is U, and here the spaces are subspaces. Here they are affine spaces.
Right.
Okay. So here whatever we are doing here. So since they are defined on subspaces, here we have to go back to the subspace somehow from V plus U. So we are using this V dash, which is there in your L dash.
Okay.
So I guess that's what is happening. I have to either entirely explain the whole concept. Better I will refer you to where I have explained it completely. From the entire affine transformation to affine mapping, linear transformation to affine mapping, I have explained it. I will refer it to you. I guess the time is going far behind. So let's wind the session up. Whatever doubts you have, please post it in Discourse. Everything will be discussed tomorrow.
Sure,
Okay.
ma'am.
Ma'am,
Thank you.
ma'am, sorry to interrupt. I have another generic query, ma'am, not relating to this, ma'am. Actually, for week 9 to 12, ma'am, for example, for week 1 to 8, we have a very book written by the IIT instructors, ma'am. Can we have any other books which is specific to that week 9 to 12, ma'am?
This is a general question asked by the students. See, week 9 to 12, in one book, everything is covered, means usually.
Just like, ma'am, for week 1 to 8, ma'am, we have IIT Madras, ma'am.
Yes, I understand. See, usually there are not many books which specifically follow the way we have covered week 9 to 12. So it's difficult to give you some specific books, but I can give you some reference. But maybe let's do it after quiz 2. Okay?
Ma'am, I want to confirm, is the session is over?
Yes, it's over.
I have not attended.
Thank you, everyone. Wish you all the best.
Thank you,
Ma'am,
ma'am.
ma'am, how to access this document that you have written?